Hey everybody, so I'm going to work through the worksheet that I gave out called More Practice Calculating pH During Titration. And so the first question asks us to write a reaction, 3 reactions, but the first part of that is to write the overall reaction. So that means from the very beginning to the end of the reaction. So you can think of that as like a net equation. So the problem says that it is between carbonic acid, so carbonic acid is listed in Appendix D, which you will have on the exam, as H2CO3. So that is reacting with potassium hydroxide. Okay. So this is an acid-base titration, of course. So the hydrogen ion in the acid is going to react with the base, and that means we're going to form water. We're also going to form a salt between the anion in the acid, which is carbonate, CO3, 2-, and the cation of the base. So the cation of the base is K, and the anion of the acid is CO3. That has a 2- charge, so that means that in order to make this a balanced compound, it has to be K2CO3. And so then our last step, of course, is going to be to balance that. I have 2 potassiums on the product side, so we have to make 2 potassium on the reactant side, which also makes 2 hydroxide, which means I'm going to also produce 2 water, and that makes sense because we had 2 protons. So there's our overall balanced reaction. And then in question B, it asks us to write the equilibrium that's occurring in the first buffer zone. So that would be the one that's occurring at Ka1. Okay, so we're starting off with H2CO3. I'm going to neglect the states of matter here, but we know what they are from the balanced equation above. And it's going to be at equilibrium with its conjugate. And of course the conjugate of carbonic acid is just what you get when you remove one of the protons. So here's our, so there's our reaction. And so the Ka for this would be Ka1, is the loss of the first proton, would be HCO3 minus times H plus divided by H2CO3. Okay. So according to Appendix D here, carbonic acid's first Ka is 4.3 times 10 to the negative 7. So this value is easy to find. And then let's see, for letter C from part 1, it tells us to do the same thing but for the second buffer zone. So in the second buffer zone we have HCO3 minus, hydrogen carbonate, and it is capable of deprotonating also to produce CO3 2- carbonate. And this would be the loss of your second proton, so that's Ka2. And And the Ka for that is listed in the appendix as 5.6 times 10 to the negative 11. That's a negative sign. I don't know what just happened with my pen here. Okay, so now I've kind of defined some facts about this titration, which is a good place to start in general. I also, and this isn't a question directly posed in the worksheet, but it's supposed to be a straight line, so let's pretend like it is. I make it a habit to sketch the graph, and sometimes I even make a little data table to help me out with that. The question says that we used a 25 milliliter sample of the original beverage, and the titration had 0.1076 molar so potassium hydroxide, and we used 32.15 milliliters. Okay, so carbonic acid is a weak acid because it has a Ka listed in the appendix. KOH, of course, is a strong base because it's a group 1 hydroxide. And so I know that between a weak base and a strong acid, I know what the shape of that curve is. It's sort of that characteristic S shape. But this is diprotic, so it's going to have sort of two S's. Okay. I didn't really mean for it to curve up at the end. So something kind of like this. And I know that the first equivalence point, the final equivalence point, which would be equivalence point 2, I know that the volume there from the problem is 32.15 milliliters. So it's relatively straightforward to figure everything else out about the graph as long as I know the volume at the final point, okay? So you sort of have to work backwards. You know the final equivalence point. You can find the first equivalence point by dividing that in half. So 32.15 divided by 2 will give you equivalence point 1, which is 16. Well, it says 0.075, but I'm going to go with 0.08 to maintain sig figs. So that's this point here, 16.08 milliliters. And I can get the first midpoint from that because I know that the midpoint is half the equivalence point. So that's going to end up being 8.04 milliliters. So that's, here. Okay, and then the final one is to find the second midpoint. And this one's a little strange because it is between two places. You can't just take the first equivalence point and divide it in half. That's not what the midpoint is. The midpoint is really literally white is difficult to see. Let's try that in some other color. The midpoint is really midway between this region, so between your equivalence point 1 and your equivalence point 2. So what we do to get that, there's two ways. You can basically realize that midpoint is going to occur 3/4 of the way through the titration, 75%. Or you can sort of get that by taking the difference, 32.15 minus 16.08, which of course should be 16.08, that gap. And then you would divide it by 2 to get 8.04. So basically that's the number of milliliters to get to your first midpoint. And then I'm going to add that to 16.08. So effectively what you're doing is taking the amount that it took to get to the first midpoint and adding it to the first equivalence point. In this fashion you can get to the same place either way. Our midpoint 2 for this problem is going to be 24.11, I think. Okay. So you can either get to that by this kind of process of inspection here, the gap divided by 2 plus the, that number plus your equivalence point. Or you can just take 32.15 times 75. And so that gets us every one of the important features of the titration. Okay, so it's all based on the volume of base. And that's what's on our x-axis, so it makes it pretty straightforward. I don't know the values of the pH yet, but I'm probably going to have to calculate that. So if we look a little farther ahead, problem 3 looks like a pH calculation. I'm just going to label the graph with where I think each part of question 3 is going to be. So 0 milliliters of base added is going to be there at the beginning. 6.35, not quite at the midpoint, so I guess, So I guess this will be B. C is 1608. Oh, that's our equivalence point 1. D is 24.1. Oh, okay, so that's midpoint 2. E is going to be 32.15 milliliters, so that's equivalence point 2. And then finally, F is 40 milliliters, which is somewhere after the equivalence point. So these are the ones we're going to calculate.